Good morning. Welcome to this video on rotating magnetic field. You must be aware of a magnetic field, lines of force that travels from north pole of a magnet to south pole of a magnet and south pole to the north pole. We call it as a magnetic field. And this word, rotating magnetic field, might sound different for you. Let us see some examples. You see three images which have commonality. Let us take up the first image. You see a needle of the clock revolving around the circular frame at a constant speed. And let us take up the second example, the planetary motion of the Earth. Earth revolves around the sun in a constant speed. The same way, if you take up the arbitrary movements of electrons, electron spins around the nucleus at a constant speed. The same thing exists in a magnetic field also. A magnetic field of constant amplitude, it rotates in a plane with a certain speed. We call it as rotating magnetic field. It means that a constant amplitude of flux taking different orientation at every instant of time. And the direction of the orientation is going to be in clockwise manner. To produce a rotating magnetic field, we need minimum of two phases displaced by 90 degrees. In the case of a three-phase system, we have three-phase windings displaced from each other by 120 degrees. And these electromagnetic coils, when they are energized, they produce a three-phase magnetic field. And each magnetic field is going to be displaced from each other by 120 degrees. And you see the orientation of the vector here. If you take up the analysis, let us analyze the vector magnetic field position at 0 instant of time. When theta is equal to 0, the first phase is going to be 0, and there exists only second phase and third phase. And if you take up the vectorial sum of the magnetic field, it is 1.5 times the maximum value of flux. Similarly, at theta is equal to 60 degree, when you consider phase 1 and phase 2 exist and phase 3 diminishes. And here also, the magnitude of flux is 1.5 times the maximum value. But the orientation of the vector displays in a different manner. If you take up theta is equal to 120 degree, first phase 1, phase 3 exists. In this case, the magnitude remains the same. It is 1.5 times the maximum value, but the orientation of the resultant vector is different. Again, displaced by some angle from the previous instant. And at last, at theta is equal to 180 degree, when you consider the magnitude remains as 1.5 times the maximum value, but again, the orientation of the resultant vector is different. For 1/2 a cycle, if you consider the orientation of the resultant vector, it has taken up a half a revolution, right, in a circular manner. This we call it as a rotating magnetic field. This movement of vector, right, this orientation of resultant vector, different instant of time, right, moving in a clockwise direction, we call it as rotating magnetic field. And the speed at which the vector rotates, we call it as synchronous speed. Synchronous speed is a constant term, or the machines are classified based on this concept only. So synchronous speed now is normally represented as ns, and the value of ns can be calculated based on the frequency of excitation and the number of poles. I'm sure all these things would have given you a good idea about rotating magnetic field. Thank you.